Hello, everybody. Let's continue our discussion about the sun. Last time we ended by calculating and using just a little bit of logic, the solar luminosity, how much energy the sun is putting out every second. That came out to a staggering number of 3.828 times 10 to the 26th watts. That's 3.828 times 10 to the 26 joules of energy every second. And then we invoked hydrostatic equilibrium to realize that that's the amount of energy that must be being produced in the core of the sun by nuclear fusion. So that leads us to now where we have to talk about what is nuclear fusion. This is going to be a two-part video where part one is going to be about what nuclear fusion is in general, and then we'll talk about the fusion reaction in the core of the sun that powers the sun itself. So our first topic right now is let's just talk about what fusion is in general. Before we get there, we have to start. I have to introduce some new terminology. Some of you might be aware of this already, but we're going to go back to atomic physics right here, and we're going to talk about the isotopes of the element. So maybe isotopes is a new word for you, unless you watch The Simpsons, and then you know that the team there is called the isotopes. But what is an isotope? So let's just go to what an atom is first, because an isotope is a type of atom. So let's go to the atom. We define the element of an atom. So what element are we talking about is defined by the number of protons in the nucleus. But we have protons and neutrons in the nucleus. So the number of protons tells you what element you are. Are you hydrogen, helium, carbon, iron, beryllium, boron? So the number of protons tells you what element you are. The number of neutrons tells you what isotope you are of a certain element. Because while there are set rules, like if you have one proton, you are hydrogen. If you have 6 protons, if an atom has 6 protons, that atom is carbon. But there aren't as strict rules on the number of neutrons that you can have. You can have a variable number of neutrons in the nucleus. And each one of those different sets. So you have, say, a carbon atom that has 6 protons and 6 neutrons. That would be one isotope of carbon. You could have carbon that has 6 protons and 7 neutrons, a different isotope of carbon. A atom that has 6 protons and 8 neutrons in the nucleus, a different isotope of carbon. So every element has several different isotopes. And I'm going to try to walk us through here. I know I just went through it with carbon, but let's go ahead and use the simplest example to show some information on the screen. Let's go through some of the isotopes of the element hydrogen. Element number 1 proton in the nucleus. So normally, you have probably heard of you probably think of hydrogen. Every time you hear the word hydrogen, you think 1 proton, 1 electron. But that's just a single isotope of hydrogen. It is the most common type of isotope. Almost all the hydrogen in the universe is this isotope of hydrogen, but it actually has a formal name of protium. So protium is an isotope of hydrogen where the nucleus has 1 proton and 0 neutrons. We could throw on a neutron. So now we have a nucleus that has 1 proton and 1 neutron. 1 proton, so it's still hydrogen, but it's a different isotope of hydrogen. It's a little bit more massive. Some people would call this heavy hydrogen, but it's technically called deuterium. So deuterium is an isotope of hydrogen where the nucleus contains 1 proton and 1 neutron. And then we can play the game again. Let's add another neutron on there. So now we have 1 proton and 2 neutrons, another isotope of hydrogen, where this isotope is called tritium, which maybe you have heard of in relation to the first nuclear bomb tests. So tritium is radioactive. It does not like to exist as tritium, and it will quickly not be tritium, and it'll change its nuclear makeup to not be tritium anymore. But tritium, 1 proton, 2 neutrons in the nucleus, is an isotope of hydrogen. Okay, we have to do that because whenever we talk about nuclear reactions, nuclear fusion, nuclear fission, then we have to talk about isotopes. So let's talk about nuclear reactions. There are two primary types of nuclear reactions. We have fusion and fission. So fusion, let's start with that one. Fusion is taking two lighter atomic nuclei and fusing them together into a single, more massive atomic nucleus. For example, taking hydrogen nuclei and fusing them together to form a helium nucleus. You take lighter elements, elements that are lower on the periodic table, and fuse them into heavier elements, elements that are higher on the periodic table. This is the process that powers stars. This is the process, this is the nuclear reaction that's happening in the core of the sun, fusing of hydrogen into helium. And the kind of inverse nuclear reaction is fission. Fission is where you have a single large atomic nucleus, a more massive atomic nucleus, and you're going to split the atom into two lighter, less massive atomic nuclei. So this one is going from a big one and splitting it into two smaller ones. And you can get energy out of this process as well if you're using the right atoms. This is the splitting of the atom. This is what powers all of the current nuclear power plants on Earth. They're all fission reactors. And what you're doing is you're taking a heavy atomic nucleus and splitting it into lighter atomic nuclei and getting energy out. So both fusion and fission can release energy. Fusion is the one that powers the stars. So let's take a look at nuclear fusion, since that's what we're going to be talking about when we're talking about what is making the stars shine, what powers the stars. So in general, a fusion reaction looks a whole lot like a chemistry reaction, like something that you would draw in a chemical reaction in a chemistry class. And the way that it works is, and the way that we write this is, we're going to have just generically nucleus 1 plus nucleus 2 fused together to become, so an arrow, we have the reactants and then we have the products. So nucleus 1 plus nucleus 2 become nucleus 3 that is more massive, than it's a heavier element, and you get energy out. So two lighter nuclei fuse to form a more massive nucleus, and you get energy out. So two protons come together to form, say, a deuteron. A deuteron would be the nucleus of a deuterium. So where does this energy come from? How do we get energy out of this reaction? Well, it comes from whenever we're binding the two nuclei together, there's going to be a fundamental change if we compare if we compare these two nuclei to what we get out. We're going to see that there is a physical difference between the two that really comes down to that if you take the mass of one proton added to the mass of the other proton, so two protons added together, that mass is greater than the mass of one deuterium nucleus. So let's say that again, just so everybody's on board. The total mass, so the mass of both of these protons added together, is greater than the mass of the product, the deuterium that you're getting out. Which means that in this fusion reaction, mass was lost. So both of these added together have more mass than what you get out. So mass is lost. The question is, what? You can't just get rid of mass. How do you get rid of mass? What happened to the lost mass? Something must have physically happened. And here we have to go to Einstein. This is one of Einstein's greatest pieces of work right here. He realized that there is a connection between mass and energy. And you have heard of this connection between mass and energy that Einstein came up with, because it's his most famous equation of all time, E equals mc squared. This connects the energy, E, to the mass that's lost in a fusion reaction, in our case that we're talking about here. So the energy equals the mass times the speed of light squared. He realized that basically mass is just sort of a condensed form of energy. that mass and energy have an equivalence to them. In fact, E equals mc squared is called the mass energy equivalence. So whoever thought that here you are at a 100 level astronomy class and you'd be dealing with E equals mc squared and hopefully starting to understand what it means and what it's used for. So really what Einstein said here is the mass energy equivalence given by E equals mc squared states that anything that has mass also has an equivalent amount of energy. And any set amount of energy could have an equivalent set, it could be uh, have an equivalent mass associated with it. That mass and energy are really just two sides of some underlying physical principle. So why is this important to fusion? How does the mass energy equivalent, how does E equals mc squared come into fusion and how we power stars? Well, we lost mass. That's what I said on the previous slide, right? Mass was lost. Well, mass wasn't really lost. Mass was just converted to its other form of energy. So the missing mass is converted to energy. In the fusion reaction, you take two lighter nuclei whose total mass, you fuse them together, and the total mass of the two lighter nuclei is greater than the product that you get out, the heavier nucleus that comes out of the fusion process. So the mass is not lost, it's just converted to energy. How much energy? We use E equals mc squared. And this is why we're about to see why fusion would be the holy grail of energy production. It's why we have been working on this for decades. We would really, 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 really like to build fusion reactions. We would like to simulate the fusion reaction that's happening in the core of the sun here on Earth, because essentially stars are just giant fusion reactors in outer space. Why would we like to do that? Let's see how efficient this is. Let's take advantage of E equals mc squared. So we can calculate how much energy is produced by fusion by looking at how much mass is lost, really how much mass got converted to energy. So let's go ahead and apply that. And let's assume that we have a paper clip right here, has a mass of about 1 gram. If we were to basically convert this paper clip, its mass to energy, how much energy is stored in this paper clip? Okay, let's run through it. We can use the energy mass equivalence. We can use E equals mc squared and just plug in the numbers. We have the mass of about 1 gram, that's about 0.001 kilograms, times the speed of light squared. Calculate that out. You end up with 9 times 10 to the 23 joules, 90 trillion joules. Okay, that's a big number, right? Let me put that in context to you. This energy, how the energy equivalent of this paperclip is 9 times 10 to the 23 joules. That energy is slightly more than the energy released by the 15 to 20 kiloton nuclear bomb that was dropped on Hiroshima during World War II. If we could convert all the mass of this paperclip to energy, it would have more energy than a nuclear bomb. You'll never look at paper clips the same way. Okay, pretty staggering, right? Let's take another example. Let's consider there's a mass loss of 15 kilograms. So again, I can convert that mass. The mass isn't really lost. It's converted into energy. How much energy is it converted into? Use E equals mc squared. Crunch through the numbers. You get a big number of 1.35 times 10 to the 18th joules. And to put that in context, that energy is roughly equivalent to the entire energy consumption of the entire world every day. Just a mass loss of 15 kilograms. You would need about 2,000 kilograms of hydrogen to fuse that into helium. If you could do that, that same reaction that powers the sun would only require about 2,000 kilograms of hydrogen to get, and if you converted that to helium, you'd get a mass loss of about 15 kilograms, and you could power the world for a day. That is a very, very, very powerful way to produce energy. So why don't we just do this? Why can't we just build fusion reactors? Well, it's because fusion is really, really hard to make happen. It requires ridiculously high temperatures to force the conditions to be fusion friendly. So let's talk about how do we get fusion to happen? And really, we're going to talk about what required temperature is required for fusion to occur. All right, so let's consider two protons. Protons each have a positive charge, right? Positive charges repel one another. They repel. If you want to know how hard they repel one another, what are the forces involved? It's called the Coulomb force, not something you have to remember for this class. But as you try to squeeze the protons together, it gets harder and harder to squeeze them tighter and tighter because they're repelling one another. The closer you get, the harder it pushes. It's an inverse square law. So the smaller the distance, the stronger the repulsive force. Okay, so it's really hard to get protons together, but they do stick together in a atomic nucleus. So how does that happen? Well, there's another force. So nuclei are held together by what's called the nuclear strong force, but that only operates on very, 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 very tiny distance scales. So you can get the nuclear strong force to take over and bind these protons together to form a nucleus if you can get the protons close enough together. But to get the protons close enough together, you have to first overcome their repulsion to one another. So you have to squeeze them. And if you squeeze these protons so they're about 10 to the minus 15th meters away from one another, ridiculously close to one another, then the nuclear strong force will take over and bind them into a nucleus. So how can we get these two protons to be within 10 to the minus 15 meters of one another? Well, we need some pretty extreme conditions. How can you get it so that two protons that are just out there in nature can run into each other and get squeezed together to be within 10 to the minus 15 meters of one another? Well, things are just moving around and they're bumping into one another. Normally, they just repel one another. However, if we crank up the temperature, and remember that an increase in temperature means an increase in the motion of particles, how fast these protons are moving. So we crank up the temperatures, and all of a sudden we've cranked up the velocities of these protons so that whenever two protons come screaming towards one another, they're moving really, really, really fast. And sure, that repulsive force is slowing them down as they approach one another. They're slowing down, slowing down. But if they had enough initial velocity, then they can get within 10 to the minus 15 meters of one another. They can overcome the Coulomb repulsion and have the strong nuclear force take over and get bound into a single nucleus. Fusion can occur. We just have to crank up the temperature. What temperature is required? You need temperatures of 10 million Kelvin or greater. 10 million Kelvin or greater will give you sufficient speeds so that you can start getting these protons to fuse together. Which means that for hydrogen into helium fusion, we have what we call a fusion ignition temperature, the minimum required temperature for fusion of hydrogen into helium to occur. And that fusion ignition temperature is 10 million Kelvin. If you're in an environment that's less than 10 million Kelvin, you cannot get fusion of hydrogen into helium. It just won't happen. Fusion requires extreme conditions. Conditions of 10 million Kelvin or greater. Where can we find 10 million Kelvin or greater sort of conditions where there are plenty of protons that are near one another? The cores of stars have sufficient temperature for that to happen. Creating that here on Earth is incredibly difficult. All right, so that's the basics of nuclear fusion. It's hard to do, but it can produce a whole lot of energy, enough to power the stars themselves, and it would revolutionize energy production here on Earth. So basically, we would never have to worry about it ever again if we could ever build good fusion reactors, because it's such an efficient way to get energy. There's pretty much no downsides to fusion reactions or control fusion reactions in a fusion uh, power plant. All right, we'll see you in the next video where we talk about the specific fusion reaction that is occurring in the sun, the so-called proton-proton chain.